CO2 sequestration refers to the capture, that is, the separation, of CO2 from a gas stream. This occurs at the surface, and then the CO2 is transported, injected, and stored in the subsurface. Otherwise, it will be emitted to the atmosphere. In terms of storing CO2 underground, there are a number of alternatives regarding geological formations when holding the CO2 underground. The most viable alternatives, and the ones that are being investigated, are depleted oil and gas reservoirs, coal bed formations that are not mineable, and also deep saline aquifers, which are not being used for other purposes, such as for drinking water.
And what the grand scheme is all about is capturing the CO2 from stationary sources, such as coal-fired power plants, separating that CO2 from other gases that may be on the stream, and then compressing it and injecting it underground in geological formation. There's a wide variety of geological formations that could be, in principle, valid for holding the CO2 in place underground, but the ones that tend to be most attractive are deep saline aquifers, and this is true for a number of reasons. The main reason is that they are the geological formations with a most poor volume where the CO2 can be sitting. So my research in this area covers the prediction of the migration of the CO2 underground.
The question that the public is most concerned about is that when the CO2 is injected underground, will it actually stay there in the long run? In principle, there are two major pathways through which the CO2 could migrate to shallow formations, and eventually to the atmosphere. Those two pathways are depicted in this slide. One of them is the presence of existing wells, some of which could be abandoned and are relatively permeable for the CO2 to migrate upwards. And the other potential pathway is the presence of active faults, or conductive fractures. This could be activated by the injection process itself. As the pressure increases in the reservoir, some of these faults could be activated and become hydraulically connected, and could provide a pathway for the CO2 to migrate.
CO2 will migrate through the underground geology, which is typically a porous and fractured medium. So that really is what my research is about, elucidating the physical mechanisms and developing mathematical and computational computer models of how that migration takes place.
In the following sequence of slides, we illustrate the mechanism of capillary trapping, by which the CO2 may become trapped and effectively immobile in the porous medium within the geological formation. This slide is a micromodel showing that we are injecting CO2 through the left inlet, and water, which fills the micromodel to begin with, is displaced through the right port. You can see that at some stage the CO2 has migrated into this micromodel, displacing the water. Now, at a later stage, the CO2 will occupy a certain fraction of the pore space, having displaced the water in the process. Once the injection of CO2 stops, we reverse the process by now injecting water through the right port, and produce CO2 and water through the left port. You can see that water is displacing CO2, and as illustrated here by the arrow, leading to the next slide, we see that water, due to surface tension effects and capillary forces, snaps the CO2 plume, leaving a blob or a bubble of CO2 behind, as seen in the center of this slide. This effectively renders the CO2 immobile.
I've been paying particular attention to the mechanism called capillary trapping. And this is a mechanism, I will not get into the details, but it's a mechanism by which the CO2 plume, which is being injected underground, as it rises up because of buoyancy, because it has a lower density than the brine originally in the pore space, this is a mechanism driven by surface tension and capillary forces by which this plume of CO2 can be chopped into smaller blobs or bubbles that do not have enough buoyancy to continue its vertical ascent, and the CO2 will therefore become immobile and trapped in the pore space. That is, of course, very beneficial because it will also enhance, well, first of all, it will contribute to the CO2 being in place underground, and it will also contribute positively to other fixation mechanisms or trapping mechanisms, such as the CO2 being dissolved in the brine and the CO2 undergoing certain chemical reactions by which it could precipitate in solid form.
In order to evaluate the impact of capillary trapping, we built a computer model of CO2 injection. What we are looking at is a representation of a geological formation in which we inject CO2 through a number of wells, indicated by the vertical bars. This illustration shows the results of computer simulation under two scenarios. On the left, the final stage of the CO2, if capillary forces were absent. And, on the right, the more realistic representation, where capillary trapping is accounted for. As illustrated on the left, if capillary trapping effects are absent, the CO2 will migrate due to buoyancy to the top of the geological formation, posing a threat for further migration upwards. As illustrated on the right, if capillary trapping effects are accounted for, you can see that there is a much more uniform distribution of CO2 that is actually trapped within the porous medium before the CO2 arrives at the top of the formation. So you can see that the clear effect of capillary forces is a safer scenario for CO2 storage underground.
The main question is that CO2 going to stay underground? That is the ultimate objective of our research program, and to establish the conditions under which that trapping, that CO2 sequestration underground will be effective. And I see this as not the only effort that should be pursued in terms of CO2 atmospheric emission mitigation and climate change mitigation, but as one that is technologically viable and that should be pursued in concert with other efforts.
Therefore, instead of escaping into the air, the captured CO2, a primary contributor to global warming, will be safely stored for centuries or even millennia